Okay, so in the last class we have discussed about this function closer of I. So closer of I is nothing but another set of items, LR items, and following certain rules. We have also seen for this grammar what will be my starting state. So we'll start the parsing action by the first item from the first production, that is s dash is dot s dollar, and from that item we calculate the closure of I. Okay, so let me write it in a printable fashion. So the first rule is start with the starting production, and we will compute the initial state by calculating the closure of initial item. Okay, then what we will do, we'll pick, so that will be my starting state. Okay, now pick one of the item from the state and move the demarcator. So here the demarcator is dot, okay, to the right. Okay, by, so it may have a terminal. So what we are doing, we are just moving the so what we are doing, we are just moving the thing, that is this dot on processing left parenthesis, we move the dot to here. Suppose if I want to process the non-terminal s, I'll move the dot to here. Okay, so in this way we'll pick one of the item from the state, okay, and from the starting state to start with, and move the demarcator by scanning one of the one of the grammar symbol. Okay, okay, now with that what we will do, either first we will create a, so to the right, let me complete it. So with this two things can happen. So one is we have created a new item, okay, from the original production. Second is we have also created a new state. Second is a new state is created which contains the closure of the new item. Okay, so whatever the new item I have created, by moving the demarcator to the right, I need to calculate the closure of that item. Okay, then the third rule is mark the edges between the two states okay, with either a terminal or a non-terminal. Okay, so whatever is the production symbol is, okay, whatever is the grammar symbol in the given production is, on consuming that grammar symbol, whether it is a T or a non-terminal X, we mark that as with that symbol. Okay, now fourthly, we'll continue this step until what? Until there are no further ways to move the demarcator. Okay, as soon as the demarcator has completed the scanning, that means it reaches here. Okay, so it reaches to the end of a given production, we continue the this three steps. Okay, now let us see a small example to see how we basically create this deterministic finite automata. Okay, so let us start with this same example. So I have, okay, so for this grammar I am trying to create the LR parse table. Okay, so how I will start with, so as I have told you, the starting item will be, so let me write it down. So the starting item will be s dash is dot s dollar. Okay, that is my I, and the first state or the starting state of the DFA will correspond to closure of I. Okay, so what will be my closure of I? Closure of I will be what? Closure of I, let me write it. So it will be first, every item of I will be in closure of I, so it will be s dash is dot s dollar. Now this s, I have already told you, if s dash uh, arrow dot s dollar is in closure of I, then s is equal to dot x will also be in closure of I, and s is equal to dot L parens, capital L, R parent will also be in closure of I by the second rule of the property of closure of I. Okay, so also dot L and dot x will also be in closure of I. So the first state represents these three LR items. Understood? Now suppose I move the demarcator by consuming the non-terminal s, then what will happen? Then the new item that will be present will be only s dash is equal to s dot dollar. Understood? Okay, and the closure of this item will only be that item only, means the closure of s dash is s dot dollar. It cannot from the grammar we can see that it can only have the same item as closure of I, no further addition is possible. Okay, now suppose I consume L parent, what will happen? So by consuming L parent, first thing by rule 1, so it will be s as dot L. Okay, will be present in closure of, this will be the starting item, then new item, and what will be the closure of this item? So it will be first start with this thing, then I have L is equal to S and L is equal to L comma S, so those two will also get added. So L is equal to dot S and L is equal to dot L comma S will also present in closure of this item. Okay, now since L is equal to dot S is present in closure of I, all the other rules where S is the LHS of the production will contribute their first item. So S is equal to dot X will also be present. Okay, S is equal to dot L will also be present, and okay, so both S is equal to dot X and S is equal to dot L will also be present. So this 5 things will constitute one state. Understood? Okay, now from here if you consume S, what will happen? If you consume S, then the items that can be possible is L is equal to S dot and no other things, I guess. So L is equal to S dot is possible by consuming the non-terminal s. Okay, so let me drag it down. Okay, now suppose I consume capital L, what will happen? So capital L presents in this production and in this production, okay, before the demarcator. So by consuming dot L, you have two rules. One is S as L dot, so the demarcator moves one place to the right, and S as and L as, sorry, it is L as L dot comma S. Understood? So this constitutes another set. So you can see here the closure of this thing is closure of, suppose this is my I0, this is my I1, this is my I2, this is my I3, and this is my I4. Then closure of, suppose this is I4, then closure of I4 is the same. Okay, I4. So there is no addition possible in closure of I. Okay, from the grammar, by studying the grammar only. So from here, if you consume the terminal token R parenthesis, what will happen? It can only result in S is equal to L dot. Okay, so no further no further addition to the closure of I. Okay, and then you can have here, if you consume comma, what will happen? If you consume a comma, then you can have, first thing will be L as L comma dot S. Okay, now since after the demarcator the the terminal is S, non-terminal is S, and for S you have two productions, so you will also include S as dot X and S as dot L. Understood? So you start with an item and you compute the state, create the new state by computing the closure of I. Okay, so the closure of that item constitutes one state. Okay, from here you then compute the dot. So by consuming, suppose S, what will happen? By consuming S, it will be L as L comma S dot. Okay, no further things is possible. Okay, now with respect to X, so suppose you get a X, what will happen? Then it will be only S as X dot. Okay, from here also if you consume X, you will reach in this state, and from here also if you consume X, you will reach in this state. Okay, from here if you consume left parenthesis, what will happen? You will reach to this state. Okay, understood? Because by consuming this left parenthesis, the only valid item for consideration is S. So the new item that will be created by consuming this left parent will be comma L parent dot L R parent. Okay, and the starting item for this state is S is equal to this thing. Okay, this is nothing but the starting item of this this state. Okay, and hence we are making an arrow, okay, that by consuming this left parent it will go to this state. Okay, so in this way, now suppose you have a left parenthesis here, what will happen? So by consuming L parent, it will again lead to what? the first item will be reached. Okay, so S is equal to dot L parent L R parent. If I consume the left parent, then I will reach the first item of this state. So it will remain in that state. Okay. So in this way we create the tables. So let us name the tables. So it will be 1, 2. Okay. Let me write it 1. Let me make it as a 2. Then this is as 3. Then this is as 4. Okay. Then this is 5 and 6, 7. Okay. 8. Okay. Then this is 9. So my new table will look like something like this. So my deterministic finite automata will look like, so this is my state 1. Okay, so let me number it 1. Okay, then on consuming L parent I go to state number 2. Okay, on consuming X I go to, sorry, this is state number 3. Suppose consuming X I go to state number 2. From 3 also, if I consume X I go there. On consuming the non-terminal S I go to state 4. Okay, and from 3 if I consume S I reach 7. Okay, then I have, suppose I consume L, then I reach state 5. From L if I hit a R parent, then I go to state 6. Okay, from 5 if I hit a comma I go to state 8, and from 8 if I hit a S, then I go to state 9. Okay, from 8 also if I hit a X I come here, and if I hit a left parent I come here. Okay, now in state 3 if I get a left parent also, I remain in the state 3. So this is the diagram for transition diagram for the DF, for the set of items which we have created here. I just number the things and make a circle. Okay, here.